Assalamualaikum and good day to Puan Sufiana. Today, I would like to present my research project, which is a review on physicochemical properties of raw and torrefied bamboo. This research study will highlight the physicochemical properties of raw and torrefied bamboo as a potential source of biofuel production, especially in Malaysia. Studies on the elemental and proximate analysis, calorific value analysis, elemental analysis, and also the chemical structure of bamboo from different sources will be reviewed. There are two objectives in this research project. The first objective is to review the physico-chemical properties of raw and torrefied bamboo, and the second objective is to review the organic chemical structure of bamboo via FTIR. The scope of this research is selected reviewed of bamboo are originally from China, Brazil, and Malaysia. And the second one is the analysis that is done in this research study is proximate analysis, elemental analysis, calorific value analysis, and lastly, the organic chemical structure of bamboo. The physicochemical properties of biomass can be upgraded by implementing torrefaction. Torrefaction is a mild treatment process in which biomass is heated in range of 200 degrees C to 300 degrees C, done in an inert environment and at atmospheric pressure. This pre-treatment process is able to reduce the major limitations of biomass such as heterogeneity, lower bulk density, lower energy density, hygroscopic behavior, and also fibrous nature. Energy originated from raw biomass is not exactly a perfect source of energy as it brings a lot of disadvantages, especially to the environment. The combustion of raw biomass is not entirely clean and it will release methane gas which will harm the Earth's ozone layer. In addition, raw material biomass is actually less efficient compared to fossil fuel in terms of energy value. In fact, some renewable sources of energy are fortified with fossil fuel to increase their efficiency. Therefore, pretreatment of raw biomass is required, such as in this study, via torrefaction, and physico-chemical properties of Malaysian bamboo should be carried out. The results shown are obtained by researchers in their study on properties of bamboos. For proximate analysis, I identified and reviewed the total moisture content, volatile matter, ash content, and fixed carbon. For total moisture, I reviewed a journal written by Xiaobao Li. In the journal, the author has done a proximate analysis on torrefied bamboo originated from northeastern Brazil, and the bamboo were divided into three sections, which are bottom, middle, and top. The moisture content varied from 15 weight% to 29 weight% depending on the section of bamboo. For volatile matter, I reviewed a journal written by Rousset et al. The author studied the percentage of volatile matter for both raw and torrefied bamboo. It can be seen that raw bamboo has high volatile matter compared to torrefied bamboo. Next is determination of ash content. In study done by Mahmoud et al., the percentage of ash content in raw Malaysian bamboo ranged from 1.09% to 1.11%. The last part in proximate analysis is to identify the percentage of fixed carbon. The data shown in the table is obtained by Roberto et al. The author study the percentage of fixed carbon for different species of bamboo. The fixed carbon varies from 17% to 23%, in which these values will indicate the level of burning, meaning that high carbon content will give slower burning and provides larger residence time compared to biomass that have lower fixed carbon. In elemental analysis, I reviewed a journal written by Wen et al. On torrefied bamboo originated from China. Based on the table, the amount of carbon increases proportionally with temperature, whereas hydrogen content is decreased when temperature increases. Thus, the OC ratio of torrefied bamboo decreased with elevated temperature, and it is proposed that bamboo deoxygenation is a primary reaction during torrefaction process. Next, I reviewed calorific value analysis done by Nazrin et al. The authors studied on torrefaction effects on two different species of nation bamboo named Bambusa vulgaris and Gigantocloa scottischini. And they found that the values of HHV is slightly higher in the node section for both species. Based on the table, the HHV values of torrefied bamboo is slightly higher due to the effect of torrefaction. The HHV of torrefied Bambusa vulgaris is 22.08 MJ per kg and 18.14 MJ per kg for node and internode sections respectively, while for Gigantocloa scottischini, its HHV value is 21.22 MJ per kg and 18.59 MJ per kg for respective sections of bamboo. HHV values highly influenced by the temperature and residence time of torrefaction. Related study done by Nazrin et al. As presented in this table, the authors determined the HHV values for Bambusa vulgaris species to be in the range of 18.90 MJ per kg and 21.91 MJ per kg. As for Gigantocloa scottischini species, the HHV values increased from 18.68 MJ per kg to 21.56 MJ per kg for temperature range of 200 degrees C to 300 degrees C. The increment in HHV values indicate the presence of lignin in the bamboo even though it underwent torrefaction treatment. The objective of Fourier transform infrared spectrometer analysis is to observe the changes in chemical structure in terms of characteristic functional groups when raw biomass undergoes torrefaction process. Based on these two figures, it shows the result of FTIR analysis done by Wahab et al. On Malaysian bamboo species named Gigantocloa brang, where the bamboo were divided into two sections which are internode and node of the bamboo. At internode section, the absorption spectra at 3412 per cm and 2899 per cm is due to the stretching vibration of OH groups and CH groups respectively. This leading to the aliphatic fractions of hemicellulose, cellulose, and also lignin. While at node section, dominant peaks bond are detected at frequencies of 3410 per cm due to OH stretching, and 1052 per cm was due to COC stretching in cellulose and hemicellulose. At frequencies 1733 per cm, a sharp bond is detected, and according to Wahab et al., this happened because of carbonyl stretching of ester and carbonyl group. In conclusion, it can be said that torrefaction of bamboo is one of the most effective pre-treatments that give a powerful impact on bamboo as an alternative source of bioenergy. Bamboo may have different properties due to its species, weather and conditions, and also source of its locations. In this review paper, bamboo from Malaysia from various species is being interpreted to see the changes of properties after undergoes treatment process. Moreover, the comparison of the properties of the bamboo from other countries was also done, and it can be said that a quite similar characteristic were observed, especially bamboo of the same species. Upon torrefaction, the physical and chemical properties of the bamboo show significant differences, and this can be proved from the data of proximate analysis and elemental analysis, as well as the resulting increase in HHV values. It can be concluded that these characteristics are relatable to each other. The amount of carbon in biomass may significantly affect the value of HHV and will certainly affect the subsequent thermal energy applications such as combustion process. Most of the journal reviewed shows the properties of bamboo from other foreign countries instead of Malaysia, even though the growth rate of this plant in this country is quite sustainable. Thus, it is suggested to future researchers to study more on raw and torrefied Malaysian bamboo and observe if there are any differences on the physicochemical properties between other bamboo with different species and origin. So, with that, I end this presentation with a bundle of thank you.